Lecture number 7, heat and the first law of thermodynamics. We have seven questions. The first question, heat capacity and specific heat, the change of fast and latent heat, the first law of thermodynamics, internal energy of ideal gas, and work and PV diagram for a gas, heat capacity of gases, and final quasi-static adiabatic expansion of a gas. In here, we will study and the physical definition of the heat capacity, specific heat, and we will study on the first law of thermodynamic definition. We write on the formula of the first law of thermodynamics, and conclusion of the formula of isoprocess formula, and applying the first law of thermodynamics for isoprocess of the gases. And the first question, heat capacity and specific heat. We know and the heat and the energy and the transferred from one system to another because the difference in the temperature. We know the heat energy flows into a substance. The temperature of the substance usually rises. And here the heat proportional is the temperature change in the mass. And here the formula of the heat equal and the heat capacity multiplied by temperature change, and we know and heat capacity formula of the heat capacity and equal, and this is heat capacity and the large C equal C small c multiplied by mass. Small c is the this is specific heat, and final formula heat equal specific heat multiplied by mass multiplied by change temperature, and heat Q equal mc delta T, and the first heat equal and specific heat capacity multiplied by change temperature, and final formula, and replace and heat capacity, final formula mass multiplied by specific heat multiplied by change temperature. And we know, and then here this C small c and specific heat, we know of the specific heat of the water and 400 approximately 4,200 200 joule divided by kilogram multiplied by Kelvin. And here this is a specific heat of the water. But in the historical unit of the heat energy, the calorie, 1 calorie equal 4.18 joule. Here, and the table and specific heat and molar specific heat of the some solids and liquids in here. And the first column and consists different chemical element from aluminium to water, and here this is different elements, solids and liquids, and aluminium, bismuth, copper, glass, gold, ice, lead, etc., and final water. And C, this is small c in here, this is specific in here specific heat C, specific heat, and the unit kilojoule divided by kilogram multiplied by Kelvin. And here this is anti-unit the calorie, kilocalorie, kilogram Kelvin. And the third this is column, and C strict molar specific heat. Molar specific heat and heat capacity per mole, and the notation of the a number of moles and a number of moles in here, and is a number of moles. And maybe we take and this is heat capacity, replace and MC and final formula we know, and molar mass divided by number of moles, and here this is m divided by n, and this is molar mass, and the C strich in here molar specific heat, and final formula molar mass multiplied by specific heat. And the table, and here this is C strich molar specific heat data, molar specific heat data for different substances in here, some solids and liquids. Okay, and the second question, change of fast and latent heat. When the heat added to ice, maybe is added to ice at, we know at ice at 0 degrees Celsius, the temperature of ice doesn't change. The ice melts. This is example of the fast change. We now enter different types of change. Include fusion and liquid to solid, melting solid to liquid. And here this is solid to liquid, maybe ice to water. And vaporization, liquid to vapor or gas. And here from water to vapor. From water, maybe water to vapor or gas. Condensation, gas or vapor to liquid. And sublimation and solid directly to vapor, as when solid carbon dioxide dry ice change to vapor. There are other types of fast change as well, such as the change of solid from one crystalline form to an crystalline form to another. Carbon under intense pressure. For example, becomes diamond. And here the factor of the temperature remains constant during the fast change, can be understood as the term of molecular theory. As the molecules and liquids are close together and they exert attractive force on each other, because between two molecules and the distance, this is small, and this is distance equal effective diameter. If the molecules in the gas are far apart, changing the substance from a liquid to a vapor requires energy to overcome the attraction between the molecules of the liquids. The energy put into the liquid to vaporize, and this increases the potential energy of the two molecules, maybe not kinetic energy. And we know, in the sense, temperature measures the kinetic energy of the molecules, and during a fast change. And here, this is table and consists normal melting point, the notation MP, latent heat, LF, latent heat of fusion, okay, normal boiling point and BP, and latent heat of vaporization, LV, for various substances, and pressure equal 1 atmosphere in here. And this is the first column and consists different chemical element from ethyl and to zinc, and we know. And what is this latent heat of fusion in here? This is formula. The heat energy required to melt, maybe and ice melt to water. I'm sorry, and ice melting is the process, and the heat energy required to melt a substance of mass m with no change in the temperature. No, the temperature is no change, is proportional to the mass of the substance in here. And latent heat of fusion equal mass of the maybe ice multiply by and latent heat and this is heat and L and latent heat of fusion of this substance. And the pressure equal in here 1 atmosphere is the latent heat of fusion for water. For water is 333.5 kilojoule divided by kilogram. And this in here this is latent heat vaporization, maybe and water to liquid to vapor, maybe for example water to vapor, and here this is when the fast change, and here this is fast change too, and different types we know liquid to water, liquid to vapor or gas, and solid to liquid, and etc. And here this is latent heat and vaporization in this formula, and the fast change and from liquid to gas, the heat required is in here heat and vaporization heat in equal mass of the gas or liquid, and latent heat of vaporization. Even now for water, pressure is the pressure 1 atmosphere, latent heat of vaporization in here 300 in here. I'm sorry, latent heat vaporization in here water 2,257 in here, and the 1 atmosphere pressure 1 atmosphere. Okay, and the third question and the first law of thermodynamics. We know the first law of thermodynamics because in here because we take one systems and this is systems, and we know, and on the added heat is a positive, and internal in the system, so in inside on the systems, and changing internal energy, and work out and work is a positive. We now, and the sum of heat added and work down the system equal the change in the internal energy of the system. The fourth law of thermodynamics, which is simply a statement of the conservation energy. In here, this is formula of the fourth law of thermodynamics, maybe, and heat added to one systems and equal and changing internal energy in the inside of the systems in plus or work out of the gases, and here the work is a positive, and the heated to the systems equals the change in internal energy of the system plus work down by the system. The fourth, in here, this is definition of the fourth law of thermodynamics. The fourth law of thermodynamics. We know, and then in here we maybe and two states, and the first states and beginning states, ending the states, and the first states and parameter of the states, the first states and P1 and B1, and the second states P2 and B2, and we know, and the measure of the energy, the flow of the one systems to another because the difference in the temperature, and this is differential form form of the first law of thermodynamics. In this equation, we now and du in the differential of the differential in here, the internal energy is a function, and however, and dq and dw is the differential of any function, the array function, and dq represents as a small amount of heat added to the systems, and work, and they represent a small amount of work done by the systems in here. And the number 4 and the internal energy of an ideal gas. We know the translation of kinetic energy K. This is the notation of kinetic energy, is the translation of kinetic energy of the molecules in an ideal gas. Is related to the absolute temperature, and increasing temperature, increasing translational kinetic energy. And in here, this is formula. And in number of moles of a gas, R, the universal gas constant. If we take, maybe we take an internal energy, the notation U equal K, and U, and here the internal energy of the gas equal translation kinetic energy, and we know the formula internal energy 3 divided by 2 N RT. And we are now, and here this is E and 3 and E, and here this is degree of freedom, because for monatomic gas E equal degree of freedom equals 3. Diatomic gas for maybe oxygen diatomic gas degree of freedom equal 5, and monatomic monatomic, diatomic, polyatomic gas, and here equal 6, and maybe we calculated internal energy. Work and the PV diagram for a gas. And this is figure and container show ideal gas confined in the container. And here this is container, and here this is piston. We entirely fitting piston with assume to be frictional. When the piston moves, in here this is gas piston of area A in here is this is small distance, and the piston, when the piston moves, the volume of the gas change. When the piston moves, the volume of the gas change is the temperature. We know, and the fourth equation of the state of the gas, and PV equal nRT. This is formula of Clapeyron-Mendeleev is the formula. If we suddenly push the piston and compress to compress the gas, the pressure will initially be greater near the piston from it, and we cannot determine such microscopic variables as the temperature, pressure, or internal energy for the entire gas systems. And however, if we move the piston slowly in small step by step, and allow equilibrium to reestablish it after each step. We cannot compress or expand the gas in such a way, and the gas is never far from an equilibrium state. In this kind of process called as quasi-static process, as the gas moves through as a series of equilibrium states. In practice, it is possible to approximate quasi-static process fairly well. And here, this is D that we enter volume, and the change of the gas, and area multiplied by dx. Work down by the gas, we know, and work the gas P pressure multiplied by the V, where is the P is the pressure, the V is, and the volume of the gas changing here. And we in here this formula work done by the gas on the piston. And we now and area multiplied by dx we replace and dv change volume change in here. And to calculate the work done by the gas during the expansion from volume 1 to volume the second, we announce the pressure varies during to expansion. And here this is PV diagram. PV diagram show and there each this is each point and PV diagram such as the P0 V0 P0 and here V0 represent a particular state of the gas and here we this is we can represent the states of the gas on diagram P versus V. And each point on the PV diagram indicates a particular state of the gas. And here this is PV diagram with a horizontal, and here horizontal line represent a series states of the all have the some value of the P, and the pressure in the constant, and this process is called isobaric expansion. We now on there for a volume of change. In here, this is volume of change because and this is area and show and change of volume. Work down is the P delta V is equal to the shaded area under the curve, shaded area in the curve in the figure. And in general, and the work done by the gas is equal to area under and PV diagram, maybe P versus V curve. And here this is work equal integral P multiplied by the V work done by a gas. And here we now and the work done by the gas as they expand an amount delta V. They are represented by shaded area P0 multiplied by dV multiplied by delta V. In here, this is a figure, and the first figure A is the gas heated and pass one gas heated. The constant pressure, and here this is constant pressure until is the volume. V2 after the constant volume in here. This is and region is a constant pressure. This is region and the constant volume, but changing pressure. In the work down along along path A is a P1 multiplied by in here multiplied by, and this is where for horizontal part we now and work down along path A in here P1 multiplied by changing volume V2 minus V1 and this is okay. Therefore horizontal part in here of the path and therefore constant volume part in here we now and the work is equal because and changing energy in here or changing volume is equal 0 and work in here this is 0. And part number B is the gas and the first cooled the gas is the first and in here this is cooled the constant volume until the pressure P2 and after the heated is a constant pressure and pass number B in this region, and this is part, and volume V2. And the work down along and pass B is a P2 multiplied by V2 minus V1, which is a much less than, and down along pass A, as it can be comparing the shaded region in here. This is region and this is region. This is comparisons and A and B. In figure number C, or C figure number pass C, and represent is a thermal expansion, meaning the temperature remains constant. Temperature remains constant. We can calculate it as a work down pass and C using formula of the equation of the state. P equal nRT multiplied by V. This is number C, and here this is a thermal expansion. We now on the formula of the for in here elementary work equal P multiplied by dV, replace and P in here. This is P, put on the formula and replace and P, and this is formula. We now the work down by the gas and the from the first volume to second volume, and the work equal integral from the first volume to second volume, P multiplied by dV. P and replace and here. And here E enter the constant put on the integral energy because in the T is a constant. T is a constant, is a thermal process. If we can remove the from integral, can remove the for and dV divided by V, and integral will be natural logarithm of the ratio the second volume divided by the first volume. Here this is a thermal the work down for is a thermal process in here. For is a thermal process. Number 6, the equation and heat capacity of the gases. We now and when heat is added to gas at a constant volume, to the constant volume, this is characterized and isochoric process. No work down, no work is down because the work is equal 0, and the heat added equals the increase in the internal energy of the gas. In here writing and heat equal heat capacity as a constant is a volume. We have heat capacity multiplied by changing temperature. A work down equals 0. And we know the first law of thermodynamics, and heat equal changing internal energy. Formula of the changing internal energy CV multiplied by dV. And here CV and CV, we obtain CV equal dt divided by du divided by dt. In the first derived internal energy to the temperature. We know and we calculate difference different than Cp minus Cv for the ideal gas. We know the definition of Cp, the heat added to the constant pressure. And for the first law of thermodynamics, and we know the for isobaric process and changing work and to replace P delta V and Q replace and Cp delta T replace, and here this is delta V we know formula A, and here du and Cp dt, and therefore investment change they become set that Cp dt, and here P dV and du I'm in here replace and du Cv multiplied by dt, and put on the formula du Cv multiplied by dt, and we know the pressure, volume, and the temperature for ideal gas. We using of the Clapeyron-Mendeleev is a formula PV equal nRT, n and number of moles. And here we and the pair in here equals 0 for ideal gas. With take the difference of the both sides of ideal gas in for the constant pressure, and here this is P dV plus V multiplied by dP, and P dV equal nR dt. the constant pressure. And here this is table show you molar heat capacity of various gases at 25 degrees Celsius. And this is monoatomic gases, different types. Monatomic, diatomic, and polyatomic gases, and molar heat capacities for the P constant, the V constant, and here this is difference Cp strich minus Cv strich and Cv strich divided by R, universal gas constant, and here this is still ratio Cp strich minus Cv divided by R. This is value for the different molar specific here for different type of gas, monatomic, diatomic, and polyatomic gases. And here on the formula, and this is formula, and this is formula. In here, this is and Cp dt, Cv dt, and P and RT divided by V. And here NR dt. In here NR dt. This is okay. And here PDV and R dt. То есть PDV, V and PDV and R dt differential, E and V, and therefore, and here, and this is dt можно, and in here this is E and therefore, and here this is Cp, and here this is Cv plus NR plus NR. Plus and R. E and internal energy formula N3 divided by 2 nRT. We know, and the heat capacity are there. For heat capacity for ideal monatomic gas Cv, heat capacity for the V constant, du divided by dt, and 3 divided by 2 nR. And Cp and put on the formula Cv in here 3 divided by nr En plus nr, and final formula for monatomic gas Cp 5 divided by 2 nr. This is for Cp for ideal monatomic gas. And the number 7, equation number 7, the quasi-static adiabatic expansion of a gas. We know, and the process and the heat flow into our systems is called out of systems is called an adiabatic process, and heat equals 0. Consider the quasi-static adiabatic expansion of the gas, and is the gas in a thermally insulated container expands slowly as a piston is doing work on it. And here we now, and then we in this is PV diagram is a show in here. This is in here. This is isotherm. The curve is isotherm. In here, this is curve is isotherm 2. This is dashed line in here, dashed line in here. Following isothermal process, but the same adiabatic expansion of the gas. In one point PV, P1, V1 in here following, and the second point on the isotherm number 2, and this is point following, and P2 and V2. This is curve, and this is line in here. This is curve adiabatic path. We can find the equation for the adiabatic curve for ideal gas using the equation of state and the first law of thermodynamics. We have, okay, we know formula of the first law of thermodynamics, and as du and replace Cv multiplied by dt, and work down by the systems, and here and PDV equals 0 because and adiabatic process heat equals 0. And here this is formula equals 0. Cv dt. We and here this is P replace on the Clapeyron Mendeleev the pressure. P equal nRT divided by V, and put on the formula on the P and equals 0. Rearranging in here gives, and here dt in here this is T, dt and here dt T and T, and rearranging gives, and 7 in here E equals 0. Equals 0 in here. And this is put on here, E and CV dt equal nRT dV divided by V. E and this is dt in here, this is 2 and 7 is 2, and organizing on the left equals 0 in here. And final formula in here, and can be simplified by nothing. We now say P minus CV equals number of moles multiplied by universal gas constant, and E and so and NR7, E and CP minus CV in final formula gamma minus 1. We now, and the gamma is the ratio of the heat capacity for the P constant divided by CV constant. We now in here CP minus CV minus 1 and RCV gamma minus 1, and here NRCV gamma minus 1, and replace in here gamma minus 1 in here dt divided by t. We then have and gamma minus 1 equals 0, and the v divided by v equals 0. And here this is natural logarithm t, and plus gamma minus 1 natural logarithm v is a constant. Using the properties of logarithm, we obtain natural logarithm tv TV and the power gamma minus 1 in the constant. And final formula and TV gamma minus 1 is a constant. This is formula quasi-static adiabatic process. Following adiabatic process, because we know formula of the quasi-static adiabatic process, and PV and power gamma is the constant for quasi-static adiabatic process 2, and work done by the gas in adiabatic expression can be calculated from the first law of thermodynamics, and we know the differential form, and dV plus P dV plus P dV in here, and since dq equals 0 we have, and dq equals 0, the W equal minus changing internal energy. We know formula of the changing internal energy, and minus CV dt, when in here we calculated work down adiabatic process, and the integral and elementary work equal minus CV dt. CV dt, and final formula CV is a constant minus CV and integral dt and the first position and the second position, and replace and delta t. This is adiabatic work. The CV is a constant. In adiabatic compression, work is down on the gas, and internal energy and temperature increase. And in here we adiabatic work we to replace delta T is the changing temperature, T the second temperature minus the first temperature, and minus in here replace and severe T1 minus T2 using formula of the equation of the state. We and the first, and here this is Clapeyron-Mendeleev formula, E and P1 V1 and R, P2 V2 and R, E and replace we now, and we now in the and R in here. This is and R divided by CP minus CV. CP minus CV divided by CV, and here, значит, 1 divided by NR in here, 1 divided by NR, and here, maybe in here, okay. And this is NR, we used and CP minus CV, and this is NR, CP minus CV. Так, CP minus CV, and here this is CV, and this is, and right in here, and CP значит, NR divided by 7 and gamma minus 1. Gamma minus 1. In here, gamma minus 1. In here, gamma minus 1. E and P1, V1. Adiabatic work is a formula, it's 2. This is a formula adiabatic work. In here, formula of as adiabatic work. This is and this is and this is adiabatic work formula 2.